Okay, welcome back to the workshop Introduction to R Programming. We worked lots on different topics for R programming over the last 3 weeks. Was everybody here over the last 3 weeks, or some you're not? Okay, so we learned lots about the basics of R. How far are you with like programming and R programming?
Total beginner for R programming.
For R programming, but you know how programming works. You had programming languages. Okay, so we're gonna go through at the beginning through some examples, some exercises that we had for the last few weeks, and I think it will be enough for you to follow those. And the most important part is your neighbor probably can tell you the URL for the workshop website, and it actually has the videos from the last sessions recorded. They're kind of long. They're always like an hour-ish long sessions, and the first session gives you an overview of R and how to use RStudio. So that's probably a good idea. And also down here, you see there is learning material, and there's lots of different resources like shorter videos and things to read where you can actually brush up pretty much by yourself over those topics. What we really talked about is like the really basic programming things, like how vectors work in R. And so if you already had programming experience, that's probably not going to be too difficult for you. Did you do MATLAB, or what kind of programming did you?
Like HTML, CSS, JavaScript.
Mm-hmm. So it's R is slightly different because there's no scalars, there's no variables that have just one value. It's all vectors. But since you know how to work with arrays, you can do it in R as well. The only big difference is the index starts with 1, not with 0, and that might confuse you initially, but once you're over this, you can use brackets and all the usual things. So we did that, and then we went through how loops work and so forth, and that's really the same as in JavaScript and so forth, so it's not a big problem. The only thing that's different is the type of, or the way that our spreadsheets, kind of like Excel spreadsheets, are stored in R. They're stored in a data frame structure, and it kind of looks like an array that has different data types in each column. But you will see that, I guess, today as well. And then we talked a little bit about cleaning and reporting, and that's the cool thing that you might be interested in, that you can build really quickly HTML-based, semi-interactive dashboards and things with R and automatic reports. You need to read up on those things. And what we're going to talk today about is how to use R for data science, meaning predictive modeling. That's kind of like our last session, our last course, where we do a little bit of linear models. Maybe I think I have a decision tree in here, and how this can be used then to put it back into dashboards and decision support and your research, or wherever you need that. Okay, before we start with data science, R for data science, let's go back to the last 2 slide sets that I had. We had here functions, loops, and arrays, and plotting, and look a little bit at the exercises that were mentioned at the end of the slide set. So if I go all the way to the end here, the last slide that we had, let me make this bigger, had exercises. And I want to go just like through, maybe here there's only 3, so that we can go through all of those. Who did those at home? You don't get a grade for it, so it doesn't really matter. Exercises, though, are really important. If you learn the programming language, you probably remember back when you did that. If you don't practice it, it's not gonna happen, right? Okay, let's go through those. It says here you're supposed to create X by using X gets random uniform 100. What does this do, you think? This one line here, and I will try to copy it. It generates 100 random numbers. It says R uniform in the R programming language. Functions that start with R and then the name of the distribution are usually creating a random variable of that distribution. So this is the uniform distribution, and 100 is the number of observations that you draw from the distribution. If I start my RStudio, then we can just paste this in here. Once it starts, hopefully it starts. Oh, I know, it's very slow. Last week it was the same. It took like 20 seconds to start. There it is. Then let's quickly do the first thing that you're supposed to do when you, it loaded here my old stuff. when you start a new project. And let me clear everything out here. You're supposed to start creating a new R script, right? And that's where all the code goes. And what I copied from my slides was this X gets R uniform 100, and then I say I want to save this file here. Wherever my projects go, I just put it on the desktop here, and I call it, what was it, chapter 3 or something. The reason again is all my code lives now in this file, and I save it, and whenever I want to know what the code was that I used, I can look it up in this file. If I type everything down here directly in R, then all those things are kind of like lost after, right? Tomorrow I will not find them, or not easily. If I make a clean file here, whenever I type something that I don't like, I can comment it out or delete it. And I have hopefully at the end here a clean script that I can run over and over again and replicate what I had as the output. So let's do this. You can push the run button here, and it executes this. And you see on the right hand side in the environment, it creates something with the name X. And if I make you small here, and it has numbers in there. It has 100 numbers. That's how it writes it. It goes from index 1 to 100, and it got the numbers 0.5, 0.4, and so forth. And those are rounded. Those numbers have more decimal places, but they are just for display, they are rounded. Can also write here X, and now X has those values, and we see it rounds here slightly differently than it does up here, but it's the same number. Okay, what are we now supposed to do with those numbers? It says here, write a function with the name average GT, probably means average grader, with two formal arguments, a vector X and a value GT, and the function computes the average of the values greater than X. So this looks very complicated, so I better copy this whole instruction down here, make it into a comment, and then probably need to break the line a little bit because my screen is so large that there's not much text that fits on my screen. So this is our instructions, the average, and then it says here write a version with and without loops. Okay. Great. Writing a function, that's already pretty advanced R code, but for lots of things, it's really helping us to make things easier. For example, if we use those lapply and apply functions that R can do, specifying an operation as a function is very important there. And functions, does anybody remember what a function needs? It needs some sort of definition that says I'm a function, right? And then it needs some code for the function and arguments. And the way to say that something is a function are, it's just a keyword function. And we are supposed to assign this function to a name. So that's easy as well. They call it here, what does it say? It's supposed to be average grader. No, spell it right. So we now assign a new function that we create, and the code will go in those curly brackets to the name average grader. In the parentheses here of a function goes exactly the same information that you use when you call a function. For example, when we call the max function, then we put in a vector of values and it gives us the maximum. So we need to specify what we want here, and the instructions tell us the function is supposed to get a vector, and we can call, and it says here the vector is supposed to be called X in the function, and then you're supposed to get a value called GT, and then it averages everything that's greater than this vector. So far so good. So we already have this. This is actually valid R code. I can execute it. And we see that in my space here, it created a function under functions that's called grader, average grader function with two arguments. And I guess if you click here, then it will show you what this function definition is. And I didn't put any code in there, so it doesn't do anything. It returns nothing. That's not great. We need to write some code for that, right? So let's go back here and let's add some code. So what do we need to do in order to average in this vector X? And I know X, I already created those random numbers. They are supposed to be compared with a number, right? And only if they're greater than that number, then we will average them. So how would we would we implement that? And I guess since you were not here last few weeks, you would say, I write a for loop and the for loop will compare something, right? And then only average if something is greater than that. Maybe sum them up and then divide them by the number of values that are greater than that. And that's a good solution. But in R, that's probably not the way we want to go, because R uses vectors and vectorization, and we would probably approach this in a different way, in a more mathematical way. So the first thing that we could do is we could see that actually we have two operations that we need to do. We need to average, because it says we need to take the average of some numbers, and we need to filter which numbers we want to average. And actually, if we filter first and then average everything that passes the filter, we have a solution for this problem. It's kind of like, you could think of it as an Excel sheet that has a column with those numbers. If I could filter out all the rows that have a number that's smaller than GT and average the rest, I have a solution for the problem, right? And Excel probably can do this, or it has an if average, if count, whatever functions it does to kind of do this. So let's do the following. We need to filter. Oops, filter. My fingers are too big for the keys. And then we need to average. How do we filter? Filtering is just another word of removing elements from a vector, right? And in R, we know we can remove elements from a vector. We can do this using subsetting, using indices, right? We could write X and then put into those brackets what elements we should keep, and how could we figure out which elements we want to keep.
Just to make sure I'm following the plot, we're looking for all elements greater than some value that we will specify.
Right, greater than this GT value.
Right, okay.
And all the values live in X, right? So we could actually say, well, let's compare X with this value greater. And everything that's greater than this greater value, this will give you a true value, right? And if it's less, it will give you a false value. And we are allowed to use a vector with trues and falses to select which elements we want from X. Let's actually try this here, because usually it's easier to try it. What value should I use for greater? Just to try it. Let's say 0.5, I guess, since this is between 0 and 1, that might make sense. So about half of the values will be roughly greater than this. And if I now execute this, X is greater than GT, then I see there's a whole bunch of falses and trues, and they hopefully correspond to the values where the value in the vector was more than 0.5 or less than 0.5, then I got a false. And if I use this to subset my whole vector, so I execute now this whole thing, then I get a set of numbers that's not 100 anymore, it's only 40, whatever, 7, roughly half of that. That's what I would expect. They all look fine, they all look like they're more than 0.5. And if I now average those, I should be actually good already, right? Okay, so in order to average those, I need to assign this to a new variable. And I could assign it to X underscore create, or create a new variable. But I can actually override and reuse the value X, the name X, because the value X here is not affecting anything outside of the function, because R is functional. It just internally here overrides the name X with a new value, but outside you won't see that. It will still be the original X value. So I can do this. And then the next thing is I need to average my X. How do I do this in R? There's a function called mean. And it just averages X. For example, if I use mean X here, then I think you average probably all of my 100 numbers. So it's probably close to 0.5, and it's 0.49, so very close. So that would work. In R, we don't need to specify the return value. The last thing that gets evaluated, that value will be returned. So since my mean X is the last function that I do in this function, whatever that returns will be also the return value of my function, because there's no code here. I could also write here return if I wanted to, but it's not necessary here. So now we have a function that hopefully, if we execute it, works. So I have still my function here. If I now look at the definition of the function, I see now it's filled out with whatever we did. So that's good. And then I would want to try this, and I would say average grader, and I would call it with the value x. X is all the numbers that we created here still. And then my grader gets a value of, let's say, 0. What do you think happens? We should get 0.5, right? 0 will say almost everything is greater than 0. The chance that a random variable between 0 and 1 is exactly 0 is very, very small. It might actually not be even in the interval that this random variable is. So it should select all the values. And if I average them, then I know that the average should be 0.49 because I did that just before. So let's do this. Looks good. Then let's average now. Let's test this a little bit more. Let's average it with 0.5. What do you think the result would be then? And then let's average it with 1. So for 0.5, if we filter out everything that's less than 0.5, then potentially all the numbers are uniformly distributed between 0.5 and 1. So we would get 0.75 roughly. So we get 0.737. So that's pretty good. And then what happens if we do this? So we filter out all the numbers that are not greater than 1, all the numbers less than 1. Since our uniform distribution goes from 0 to 1, there should be no elements. And I guess, I don't know what mean does, but I think when mean gets no elements, it gets kind of desperate. And it will maybe give us some not available, some weird value, hopefully. Not 0, because 0 should not be, because all numbers have to be more than 1, so 0 is probably not good. And it gives us not a number, NaN. And the reason is because if I filter it out, it figures out there's 0 elements that match this, but we know that the averaging function sums up the values, divides by the number of elements. But if I divide by 0, then I get an invalid division. And R, instead of having an exception or anything, just says, what you get is not a number, because in math, dividing by 0 is a no-go. We don't do that. So this is why you get NaN. Okay, so defining functions is actually pretty straightforward. We did a function here that's really not very complicated, but using small functions to solve bigger problems is a very powerful thing in programming, and also especially in functional programming like R. You can get by with writing 5 very tiny functions where the chance that you make a mistake is very small, and you can put them together to solve something pretty complicated. Okay, I don't want to do this with a for loop. Of course, you can program it the same way you would do it in C++ or JavaScript with a for loop. But that's not the way to go in R, because you already have all those things in front of you that you can use to solve this problem way more elegantly and with less chances of errors. Let's ignore the other 2 ones. If you have time at home and you want to practice more, you can do those 2 things. They're not too hard. Let's go to the plotting examples here, the base plots in R, and let's look what the exercises here were. Let's see which one we should do. I think we should not do the first one. It's fun to plot sine x over x, but it's not necessarily the most illuminating R code that we have. But the second and the third problems are pretty good, and they will give us a segue into what we're going to do today, which is predictive modeling. So the first one, let me actually copy both of them and put them into my R here. And this is plot cars, scatter plot. Plot all data points. It's a long instruction. And then plot histogram. So this is a different problem here. So this was problem 2. So it says there is a cars data set that has speeds of cars and distances it takes the cars to stop, which is pretty important, right? Because you don't want to run into the person in front of you, or your insurance company will not like you very much and charge you more money. So there is different distances that different cars take, depending on what kind of weight they have, what kind of brakes and all kinds of things. And there is a data set. In R, there are some built-in data sets that people use to teach classes like this course or play with. And one is the cars data set. And if I say question mark cars, then it gives me here the description. It says This is a data set for stopping distances. It was recorded in 1920. So the cars that we have in there, they probably didn't break in the same way that cars nowadays do, right? And the distances will be probably a lot longer, but it's still good to play with. It says it has 50 observations, means 50 cars. And then you have speed in miles per hour and distance in feet. And there's some examples here, so that's pretty good. And let's try to do this. If we want an internal data set, then we say cars, and this will load this data set. And we now see all of a sudden we have cars here. Don't worry about this. This looks weird, but it just says that R is lazy and didn't actually load it. It loaded something that's called a promise, which means that if I use this data set, it knows where it finds it. It just has not loaded it yet. Lots of programming languages nowadays become lazy and lazy, kind of like our students. And they do things not when they're supposed to do it. They do it right before it's too late, right? Hopefully. Okay, so let's deal with these cars. Let's look at the cars data set, and we can do lots of things. We learned we can do head, which gives us the first few rows of cars, and then all of a sudden you see now R got desperate and says, no, yeah, I know it's a data frame, and I really loaded it because you really asked me for obtaining the promise here. And we see that the answer here is, it seems to be a table with those two columns. It has speed and distances, and the description is it's in mile per hours and in feet. We also can do summary cars. Then we get the statistical summary. They're both numbers, so you get minimum, maximum, and some statistics here. And something that we learned that's really useful in R is str for string representation of the data structure. And it says it is a data frame. It has 50 observations and 2 variables. And then my first column, since it's stored, actually it's a list. My first list element is called speed. It's filled with numeric numbers, and here are some examples of the first few numbers, and my second column is dist, and it also has numbers, and here are those numbers. So this is really how it's internally structured. So far, so good. So now we can go to the next thing. It says plot the car data set as a scatter plot. How do we do this? Well, in R, there's a plot function, right? The first thing that you probably should try is just take the data and say plot and see what happens, right? And so I just take cars and plot and see what happens. If it's not what I like, then I need to probably read the instructions and do it again. But luckily, it gives me actually something that's very close to what I want. It says here, there's my x-axis is speed, my y-axis is dist, and it's a scatter plot. It has those points. Each point here represents a car with its speed and its braking distance. And obviously there's some relationship between speed and braking distance. The faster you go, the longer it takes you to brake. And it looks kind of like either it's linear or maybe not linear, depending on how you understand the physics behind braking and friction and all the things that you need for braking. So that's good. It actually gives us the answer that we want. And the reason is, if it finds a data frame that has only 2 columns, it will just give you a scatter plot of those 2 columns if those are numbers, because R knows if you have 2 numbers, that's probably what you want as a plot. If you have more columns, and we will see data set later like that, then it will make maybe a matrix of lots of scatter plots or whatever the thing is that's appropriate here. So that's good. But now what we want to do is, it says here all data points with a distance taken to stop greater than 80 should be colored in red, with the idea maybe that it's dangerous if it takes more than 80 feet to stop. And we want to mark them red so that we know which ones those are. With a braking distance. If you look back at our plot, which ones of those dots would be colored red? Because it's always good to have an idea beforehand to know what the output is that I want, and then I can later on check if it really does this. Well, we have here speed, right? And then we have distance, and the distance of 80 is here. So everything that's above this line here should be colored red, and it's dangerous because the braking distance is too long. That's good. We understand the problem. How do we do this? For people who were here last time, we looked through the slide set, right? And there's lots of graphical parameters that you can use for your plot function. And you can, for example, look here, plot. And then it hopefully gives you the help page down here. And it says that this is actually the generic function, but really what we use for simple scale plots is this plot default. So we click on this, and then we see that the function here has a whole bunch of arguments that we can have, and we have to go through them. But I'm too lazy, so I just type here color, because I want to do something with color, right? And it says here, yes, there's an argument called COL, and it colors lines and points, and that's really what I want to do. So I want to do this, and it probably comes somewhere in here, but I usually am not good at reading. I have a very short attention span, so I say, you told me color is good, so let me do color. Okay, and let me first try something. Let me say, what if I say red? Well, then everything is red. So at least it changes the color, maybe not the way that I wanted to. So next try. What if I say 2? Then it's also red. What if I say 3? Then it becomes green. What if I say 1? Then it's black. If I say 0, invisible, that's great. So I guess that's not what we want to do. And it seems that the default was actually 1. It's this black color. And 2 is red. So now what we need to do is we need to figure out which points we want to color. And the way that plotting works is it looks at the first point, plots the first point. And first point is defined as, if I go back to the head here, as the first row here. So this is the first point that it's going to plot at 4 and 2. So it's probably this one here. Then it's got a 4 and 10. Those might not be ordered in any way. Here, I think they're ordered by speed, but they could also be sorted by something else. The plot will be the same no matter how it's ordered. So what we now need is kind of like additional information about color. And one thing that we could do is we could add here another column that specifies the color and would say here, oh, this can be black, this can be black, they can all be black. And once the distance is more than 80, it should say red or something like that. Can we do that? We probably, with some Googling, we will probably be able to do this. Luckily, we don't need to necessarily do it. All we need to understand is that really what we need is a column here, which is just a vector that has the same number of elements as our data set that tells us if the color should be red or black. And we can do this by just calculating this value. And all we need to do is we need to write here now a logical expression that checks if we should color a data point red or black, given I guess we only need the speed, right? Only the distance. So we have here our cars data set, and we can look at distance. This is one way I can specify a column in my data frame. So I get just the distances cut out, and my distance needs to be greater than 80, right? So let's just try. What happens if I do this? Let's see. This is not bad. It's not exactly what I wanted because all my other points are gone, but it really focuses on those points, right? But I want those red and the other ones not. Let's now check out what this thing here did. It gave us actually a logical vector. And so how can plot know that it's supposed to not plot the things that are false and yes, plot the things that are true? Well, maybe it's built in and it says you can give it a color false and then it knows this is not really a color, but that's actually not how it works. It translates those logical values into numbers because plot says, I know how to call numbers, call colors by number. 0 is black, 0 is nothing, 1 is black, 2 is red, or by name. And what it does, it says, I have here logical numbers. The next best thing that I can do as a programmer is defining that false is nothing, so it's 0, and true is something, so it's 1. And we remember 1 was black, that's why those are plotted black, and 0, false was 0, so that's why all of those kind of like disappeared. So now a quick trick for this is, if I take this here and say s.numeric, then I get exactly this translation that R does internally, but I can also then just add numbers. I could add 1 to it. And then I don't have a 0 because 0 is bad because it makes things invisible. I know 2 is red. It made everything that was true here red, so maybe that is what I want. And so I can do this up here and execute this line. And then I have hopefully the answer that I was looking for. Those dots are a little small, but everything up here is red and everything else is black. So what you do here is you add some kind of conditional thing that looks at each row, decides based on the distance in each row if something should be red or black. And you do this kind of in a very tricky way by using true and false and then saying, oh, those are numbers, and plot understands numbers. If you want to make this a little bit trickier, you can write an if statement and can actually use the word black and red or green, whatever you want, and don't need to resort to this kind of like number jumbling. Okay, so far so good. Let's now go to the.
Say if you want this symbol to be different for different values.
Oh, you want maybe like down here green and then orange and red is bad or something like this. So what you would do is there's a function called if else. And this is very similar to the if in Excel, where you can state here, I have an if else a test, and then I have yes and no. For example, I could write this here as if else. My conditional test is the speed more than 80? And then I say, if it is more than 80, I make it red. If it's less than 80, I make it green. So I use exactly this syntax here. This is the result that you get for yes, and the second one is the result that you get for no. And then I could try this. I forgot there's another parenthesis that I need to add to make it actually valid code. Okay, let's go down here. And then my result looks like this, right? And so if you want more than this, you would have to put an if-else statement inside the other if-else statement, kind of like what SQL does and so forth. Not very fun. Also, there's a case statement that might help you with that problem, similar like in other programming languages. Okay, this is probably the better readable version than what I showed you before, because it explicitly says, oh, there's an if statement in there, and there's real names for colors. But since if you work with a programming language a long time, you do the shortcut that's the least painful. That's why I showed you the other version first. Okay, last thing. Making a histogram of speed and distance. How do I do that? Because maybe I'm interested in the distribution of different speeds and distances in this data set. Well, I need to figure out what histogram does. So I could say let's actually do this here. Go to help, say histogram up here, and then hopefully it searches. And it says here, there's all kinds of weird things. Weird things is there nothing that's simple. Let this histogram does it not come up at all? Oh, here, this is actually the one that I was looking for. This first name here is the package, then there's colons, and then there's the name. And graphics is the package that actually is the built-in base R graphics. And there's a function called hist, and it says histograms. So let's go there, and it says histogram, it gets a vector X. You probably can go down to the examples here and run some of the examples to see what this does. So let's try this and say histogram gets X. Is this going to be good for us, you think? Probably not, because it's called cars. Is this not good? Let's try it. Oh, it says that's bad. It says here X must be numeric, and with X it means its first argument here. So this is kind of confusing. It means this argument here is called X, but we actually use cars for X. So be careful here, although it says in his default cars, X is the problem, even though we never had an X here, it's just because it calls this argument that way. And it wants it to be numeric, but this car is not numeric. The problem with cars is that it's a data frame, right? It's not just like one variable, but you need one variable, so you need to pick which variable you want. And so let's use, if I push taller, then it gives me choices here. Let's do speed. And then it's already pretty happy because it gives me a standard histogram, and it figures out how many brackets it wants to make, how many buckets it wants to make with cars. And it seems most of the cars are in a speed distance, have a speed from 10 to 20. It was miles per hour, and I can do the same thing for for my distance. And then the histogram looks slightly different. The largest number of cars have a braking distance of 20 to 40. And that depends on the speed, of course. Okay, so far so good. So we can make all those plots and then you can put them in reports of whatever you want, or you can use them just to analyze the data. So far so good. Now let's go to data science. All the things that we did so far in R, you need those for data science, right? You need to be able to import your data, you need to be able to clean your data, you need to be able to analyze your data, maybe write some fancy functions like this grader or whatever, average grader function. Definitely you need to be able to make scatter plots and histograms to look at the data. Often you use those just to find out there's outliers in the data or dirty data in there. So we need all of those. And then we can finally make the step, go to the fancy and cool thing, which is predictive modeling. And this is what I want to talk about today mostly. Okay, here we go. Number 5. First, what is data science? Quick answer is nobody really knows. Data science is like, it obviously has data in it, and some people do science, and then you have data science. There is some definitions that are evolving, but they're not quite clear. For example, Halvarian, very important person, says it is pretty much everything that has to do with data, and he says the ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, and it's going to be super important, right? So that's great. So basically everything what statisticians did, what computer scientists do, what I guess communicating, what like marketing and communication specialists do, and visualization all the way to artists, right? That make very fancy and pretty visualizations, all of that is data science. And now you could argue each individual part is data science, or only if you do all those things together, it's data science, and we are not quite sure. I guess a statistician is a data scientist that does a part of those things, or a computer scientist is a data scientist that focuses on processing data in some way, right? Or some visualization specialist and communication specialist is potentially a partial data scientist because he or she does just that. What are the things that we do in data science? And I stole those here from UC Berkeley. They made a really nice chart. This is kind of like a flow chart of what those things that Halvarian said here mean. And so they start with capturing data, acquiring data, data entry, finding signals and all so forth. Then this goes into some maintenance states where you have data warehouses and SQL databases and we store it internally in R with data frames. And then we get to the area of what we're talking about now today, which is processing the data in terms of data mining and clustering and classification and summarizing the data, exploring the data, finding maybe some linear regression in our data. And the data set that we just saw kind of looks like we could do some regression between braking distance and speed. And then this goes to communication, where we write a report, or it could also be implement some sort of like dashboard to give a manager insights that then the manager can use to make decisions. And we learn a lot in this process and usually go back to capture and kind of make a second kind of like improved project that improves all those steps, or we figure out there's other things where data science can help, and we do over and over this kind of like cycle of more projects. Okay, so far so good. We actually covered lots of those things. Communication we covered in the way that we did some basic visualizations. We covered data capturing entry because we looked at how to read Excel files and how to get those. And so we covered those a little bit. And the only thing that's missing is this predictive modeling. What is now predictive modeling? There's lots of names that were used. Initially, this whole area started with artificial intelligence quite a while ago, where we thought that we could build like some robot that can be like a human, right? And like be self-aware and act autonomously. That did not work out yet, but who knows, right? Hollywood it worked, but that didn't turn out so well for us because they killed us all then after a while. So this is where it came from. And then for a while, data mining was the biggest thing. And now data mining, the word kind of like went to the background in favor of analytics and data science and machine learning. And machine learning got so much attention, because part of machine learning is language understanding and also all those visual things like looking at images. And this is really, really exciting, right? Because if I can talk to my phone and the phone gives me answers, that's super exciting. Or if my car can drive by itself because it can see stop signs, that's super exciting. And this is why kind of deep learning and machine learning is so important nowadays. The truth, though, is that there is very little difference between data mining, machine learning, artificial intelligence, and a large part of the technical side of data science. They all use exactly the same models, they use the same data, they use the same process of how to do things, and they also use the same tools. So it's the same thing. And usually, if you ask somebody, are you a data scientist? And then they will ask you, does the job description say data scientist? Yes, then I'm a data scientist. If it says machine learning, then I'm a machine learning person, right? Okay, so that's really very similar. And the things that we want to look at today is how to make predictions, how to take data and then make predictions, because that's really important. For example, if you look at student outcomes, if I could predict early on that a student will have next semester problems with the courses that they're taking, then I can already do something proactively. If I'm just, I don't know, then probably after the next semester, it's going to be way harder to fix the problem as before. So prediction is a very, very important thing. And there's two basic areas of prediction. One is where your prediction result is supposed to be a number. For example, you predict the height of somebody or the weight of somebody or some score, right? And the other one is called classification, where you predict, instead of a number, you predict the label. So usually you predict yes or no. For example, will the student pass the class next semester? Yes, no. And the regression problem would be, what is the score that the student gets between 0 and 100 for the grade? Those are related with each other, because if I know that if your score is better than 50, you're going to pass, then I can translate one into the other, right? If I can predict the score that the student has, and I know what the threshold is for passing a class, I can easily translate this into a classification problem. So those two are related. They use actually similar algorithms, but they're usually kept apart, because measuring how good they work, how well they work is slightly different. And we will look at mostly regression here. And I think in the exercises, you have one exercise that you can try for classification. So what is now the usual predictive modeling framework? What kind of data do we need? And what kind of outcomes can we expect? So usually what you have is you have a training set. And the training set here contains data. And I have here a different cars data set. It doesn't have the braking distance and so forth, but it has actually the weight of cars and the horsepower. And it has one special column here, which is called miles per gallon. And this is my so-called response. This is what I'm really interested in, because we know that being green with your cars is important, right? And there's all kinds of regulations that in the next 10 years, the miles per gallon have to go up and so forth. So maybe there could be a relationship. If a car is heavier, it probably is not so good with fuel economy, right? Or if it has lots of horsepower and it's like this muscle car, it's probably also not so great for the miles per gallon. So one option could be that a car maker considers creating a new car, and they know that the car that the customer wants has this weight and has this horsepower. Can I use this data to kind of predict what is the most likely mile per gallon that I can get for those cars if we use the same technology as for my other cars? So this could be my thing. And those are the training sets. So those are all the cars that I currently produce. So I know exactly what their miles per gallon is, and I know exactly what their weight is and so forth. And the idea now is that I take this data and I train a model that can later on answer questions where I give you the information about a new car, and it spits out, this is the mile per gallon that I think this new car will have. And this process is called prediction, where you take a model, you have new car, a new data, where you, for example, for those cars only know their weight and their horsepower, but you don't know what their miles per gallon is. And you put those together, and the algorithm will spit out a prediction, which is just the missing column here. There's miles per gallon column, where it says this car most likely will have a consumption of 21, or will go 21 miles per gallon. So this is kind of the idea. And there's all kinds of other applications, right? This could be students and some kind of learning outcomes. This could be medical information and some score for some disease, diabetes, whatever it is. So there's lots of applications for this. Or it could be all the kind of things that you do, and you get a credit score, right? And the bank wants to predict your credit score, and that's really how credit scoring works. They use exactly this kind of thing. They have lots of people that paid their loans and defaulted on their loans, and they put those into this kind of like spreadsheet, learn the model, and now they use your data to predict if you are likely to default or not default, and they actually give you this credit rating and credit score that is supposed to tell us how creditworthy you are. Okay, very good. So how is this now in R? And I overlay here the things from R that we use for those. So obviously this data here is stored in a data frame, right? Because it has columns and the rows are our cars here. Looks like a data frame. Some of those columns might be labels, might be male, female, if it's medical, or it might be for cars, the color of the car. Although I'm not sure that the color has influence on the miles per gallon. Who knows? But it might be some number of, has it turbocharger or not? So it's more kind of like a label, yes, not. So that might be in here. Then our train function is really just a function in R, similar to what we implemented ourselves, just probably a lot more complicated. And they're already available in R. Then what we get back is the model, and this is just a regular R object. Usually it's just a list of elements, whatever this model has to have, and we will see how that looks like. Then our prediction is another function that R provides for us. Our new data is a data frame that just is missing this last column, and our predictions usually is just a vector that represents this kind of like predicted column. So we know all the data structures now that are used in this process, and we can actually start trying an example. So the data set that I use here is called MT cars. So it's a different data set than the cars data set. And it has the following information. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 columns. The first one is the miles per gallon. We know this is kind of what we're interested in. And then it has the number of cylinders, the displacement, the horsepower, I have no idea what D-RAT is, but I'm sure it's important. The weight in, I think this is in thousands of pounds or in tons or whatever it is. Then some acceleration and if what the carburetor does and how many gears and so forth. So it has lots of different information about the car, and we assume that this information tells us something about how fuel efficient the car will be. Maybe if you remember what this kind of thing does, last time we talked about Markdown, and this knitter cable is just a way to make a regular R table in Markdown look pretty. And since my slides are made with Markdown, that's why I use this here. And you see that this table looks not just like our output, it looks like a pretty formative table. And we look here at head, so there's actually way more cars, right? It's just the first 6 rows are shown here, but there is, I think, 150 or whatever cars in the data set. Okay, now I can start plotting something very similar to what we saw before. What I want to plot here is the weight by the miles per gallon. So it puts here on the X is the weight, and Y-axis is mile per gallon. I actually have to write which columns I want because there's so many columns, and plot will do like a matrix of lots of scatter plots, and I wanted to only look at this one. And we already see that the weight of the car is really not good for your fuel economy. Because if the weight goes up to 5 tons, I don't know who has a car that weighs 5 tons or 5,000 pounds. Is pounds and tons. I think imperial tons are different than metric tons. I don't know, but it's definitely not good, right? Because the miles per gallon goes down to 10 or something. That's ridiculous. Unless you like sports cars, then it's probably okay. And it goes up to 80, and those are really light cars that are probably built to be very fuel efficient. And it seems there's some sort of relationship, and we could assume maybe, or is this linear? Maybe it's not linear. Who knows? First assumption usually is that we do is it looks kind of linear. Linear models are really easy to handle, so let's do a linear model. And in our linear regression is really just a training function that's called LM for linear model, and you can look it up with !LM. And then what it gets is a data set, and we use the mCars data set, that's the easy part. And then it needs this description of the model, of what I want to model. Because my data set has lots of columns, we saw here. It has 7, and we need to tell the linear model which of those columns is the one that I want to predict, and what are the columns that I'm supposed to use for the prediction purposes. And this is what this thing here does. It's called the formula interface. In R, lots of functions use consistently the same type of interface. And the way that you formulate this, you always write the column that you want to predict first, then you have this squiggly line, and then you have a definition of the columns that the model is allowed to use to make the prediction. And I'm very restrictive here. I say, I only want to use the weight column to predict my miles per gallon. And the idea, I got the idea because this looked like a really nice relationship, right? The weight goes up and consistently the miles per gallon go down. So you get this function. If I look at the model that I get here, then this is how the model looks like. It says, this is how you called me. You gave me this formula, and I have an intercept of 37, and I have a slope of minus 5.34 depending on the weight. So whenever the weight goes up 1 unit, my miles per gallon go down by 5 units. That's kind of like how we interpret these linear models. If you do summary, you get the standard statistics output that a statistician would expect from a linear model. You get all those kind of like statistical tests, and yes, those are all statistically significant. You get lots of stars, right? The p-value is very small. So it seems to be a good model. You get an R squared, 12.7 is not too bad either, and some F statistic. And if you really like those, you can read up on those, right? So if we now look at the model itself, we can also look at the fields and the representation of the model itself, because this summary just gives you a nice kind of description of all the values here. But if you look at what's really in there, you see that actually this model is stored as an R object, as a list with 12 elements. The first element is just coefficients, and it's just a vector with 37.29 and minus 5.3, and those are really those elements that you see here, the coefficients. And then it stores lots of other things like residuals and effects and rank and some other things that people who work with linear regression understand what they mean. And they tell you probably something about if the model is appropriate or not, and if there's like some correlation between things where it shouldn't be, and all those kinds of things. I don't want to go too much into this, but what you can do is you could say model $ coefficients, and you would get this vector. You would be able to extract different information from this R object if you need to. Okay, how do I now use this model? Well, I can plot again my scatter plot. That's my first line, and then I can add a line here, and a B line does the appropriate thing. I had to experiment a little bit and Google to find out how this works. And I give my line function the coefficients of model, and it will automatically add this line here. And I just said I want it red, and I want the line type to be dashed. Number 2 makes it dashed. And I want it to be a little thicker so it's easy to see. So I made the line with 3. And this is now the linear regression result with an intercept of close to 30 and the slope of minus 5 that explains the data. So far so good. Hooray, we have some model for our data. Maybe using just the weight is not really the greatest model because the other variables have influence too. And so I added here a few more, and now we get, instead of simple linear regression, we got multiple linear regression. So I added here the number of cylinders and the horsepower, and it gives me a model that says if the weight goes up, if the number of cylinders goes up, or the horsepower goes up, that's all bad for your fuel economy. If you look at the statistics here, it actually really thinks that weight is the only thing that's highly significant, and the others are kind of like, not so great. So it didn't make much of an improvement. Let's now look at how we do prediction, because it's supposed to be a predictive model, right? I'm supposed to give it a new car where we don't know what the miles per gallons are, and it should tell us what they are. And in R, the technical part is easy because all models have a function called predict. You give it the model, you give it new data, and in this case, I give it the first six cars of empty cars, and it will just spit out the prediction. It will just say, yeah, my linear model predicts that the Mazda RX-4 has 23 miles per gallon. And for the Mazda RX-4 WHE, I don't know, it's less fuel efficient. I guess it's heavier, probably. Okay, so that's easy. Once you have a model, no matter what the model is, you can use the predict, give it new data, and it will spit out the prediction. Okay, what is now the downside of what we just saw here? Well, I used all the cars and empty cars to learn my model, and now I predict the first 6 cars of the same data set, and that's usually not what you want to do. If you want to be honest, right, for example, with students, then I will not give you 100 questions, you study them, and then I ask you those 100 questions again, right? I will probably give you 100 questions out of the 150 that I have. You can study them, and then I give you 50 other questions, right? And then we see if you can apply the concepts. And you want to do the same thing for predictive modeling as well. Statistics like linear regression uses something called in-model validation things and gives you this R squared, but that's not how machine learning people do it. Machine learning people take the data set, cut it into a training set and a testing set, then train on this set and test on the other one and see how good it is. And this is kind of like painful to do, but luckily in R, there is packages like Current, MLR3 for machine learning in R, I guess 3, and Superlearner that do those things for you, and you don't have to worry too much about how to do this in the correct way. And I want to just look at Carrot, how this can be done. So I'm still training a model that says I want to predict the miles per gallon depending on the weight, the cylinders, and the horsepower. The data is still empty cars. The only thing that I add here is that my method is LM because Carrot provides a function train, and it can train all kinds of models. They have like hundreds of different types of models that you can train. And all you need to do usually is just change this method and say, maybe I don't want the linear model, but I want some other type of model. So it trains all the same thing, but it does a lot of more work. It takes longer for this function here to run because actually it doesn't train the model once. It trains it, in this case, 25 times. And it uses bootstrapping to separate the data set into a training set and a test set randomly. Then it trains, tests on the test set, and then does the same process again. It takes a different subset for training and a different subset for testing, and it does this 25 times. And so it gets actually 25 models, it gets 25 results, and then it uses them to calculate error statistics on these unseen test data sets. And it says, for example, here, the root mean squared error, which is one of the typical ways to measure the difference between the true value and the predicted value, is 2.8. The R squared on this whole lot sample is 0.84, so this is actually pretty good. And the mean whatever error, what is it? It's the median average error, something like that. You have to look that up, is 2.3. For all of those things, other than R squared, smaller is better. Smaller errors are better, and R squared is supposed to go to 1, then that's good. So that's pretty good. It does this for us, and those are really good scores to tell us how good the model really is. If we now go to a different model, for example, if we say maybe linear model is not good, and let's use a regression tree, which is a complete different type of model. It makes some kind of like decision tree, and in each node it tells you what the average miles per gallon for a car is. Then all you really change is you write here instead of LM R part. And it will train a different model. It will still do bootstrapping. It will give you here lots of statistics. The regression tree actually has some free parameters, CP for complexity, and it tries different values and says, you know, if I set this value to 0, this is my error. If I set it to 0.97, this is the error. It figures out it goes up, so that's not a good strategy. So it says it chooses actually the one at CP is 0. So it does parameter tuning and this holdout evaluation for you. This tree that we get, we can actually look at it, this classification tree, and this is kind of how this tree looks like. It starts up here with all the cars. That's why it says 100% of all my cars are up here. And the first decision that it makes is it looks if the cylinder number is more than 5. If it's more than 5, it goes to yes, down here. If it's less than 5, it goes down here. And if it's less than 5, then its best prediction that it can do is 27 miles per gallon. It's very, very discrete, the whole process, because you have just this decision and then you get just one value. And it says 34% of my cars fall into this block, and I predict 27 for all of them. So that's not very, very, very detailed, right? If there's more than 5, then we have 66% left of the data, and then we look at the horsepower. If the horsepower is close to 200 or more, then it's only 13. And if the horsepower is less than 200, then we have 18. So there's actually only 3 values that it really predicts. And that's why the root mean squared error is not really great. It's 4.0. It's way worse than the 2.8 that the linear regression was able to do. Those models might also give us variable importance. That's a very important question often, to figure out what variables are really driving this decision. And here it says horsepower is the main driver in this decision. And then you have the cylinders, and the weight actually has no value. It has a value of 0 in this decision. And the reason is because we never use weight to make any decision, which is really strange because the linear program, linear regression, says actually that weight is the most important one and cylinders and horsepower is actually not. And what we see here is that depending on what model we use, it might look at completely different parts of the data. And we don't know what the right thing is. Probably horsepower and weight are related with each other, right? Because heavier cars need more horsepower, so people would not build a really heavy car with no horsepower. And so if you have this relationship, then the algorithm might have some preference to use one of the two correlated variables, or the multiple linear regression probably we violated lots of things where you're not supposed to have correlated variables as the input. So you need to be more careful there. Okay, this is actually all that I have here for our predictive models. They're really straightforward to use. And I have a couple exercises that you can do later on. What I want to show you still before we close is where do I find what kind of stuff can I put in this method thing, right? Because if it's so easy to train other models, then how do I know which models I can train? And I think, unfortunately, I didn't put a link here, so I will show you where I get this information. And then you can show whoever is the person that you give your model to can show how cool you are, because I use the most fancy model there is. Nobody understands how it works, but it's wonderful, right? So if you go back to the website here, it says here, tutorial carrot predictive modeling, and you can look at that. And here it says documentation, the carrot package, and here it says available models. So if you go to that, then you get a table for different models. And this table, if you look at it, looks very much like a markdown table, right? Similar to the tables that we used in our things. And you can see here, if you scroll down, that there is, does it let me scroll down? No, it doesn't, so I have to roll down. We see there's quite a lot of models. Let me track this down, no? And maybe at the end here it will tell me how many. So this is all the models that Carrot supports, and it says here there's 238 different predictive models, which is great if you like choice. It's probably not so great if you have to choose one out of those, right? And so there's two important things. Some work for regression, some work for classification. And I told you before, the difference is regression gives you a number as the answer, classification gives you a label as the answer. Some of them are good for both. And then they have information about what additional variables they use and so forth. And what most people do is they have a preferred set of maybe 10 models, and they will take the data, throw all 10 models up at them, look at the error numbers, and just take the one that has the lowest error and say, oh, for this data, I use a linear model. For that data, I use a tree and so forth. And the only reasoning that they use is, oh, on my test set, it worked better. And unfortunately, in machine learning, that's where we got to. In statistics, people will tell you why they use a certain model and say, this is just, you cannot do this. This is the right one. In machine learning, that's not the case. Each type of model has some sort of bias of what kind of structure it can learn. And if your data has this structure, then this model will perform well. If the data doesn't have the structure, but structure that's good for another model, then the other model will work well. Since all our data usually is high dimensional, we have no idea, no way to look at the structure and see, oh, this is obviously a linear relationship, and that's why a linear model works. That's why it's kind of so hard in machine learning. But the tools are great because you can, within like maybe half a day, test 20 of those models, make a table, and say, you know, those models work well, this one didn't, so let me pick the one that works the best and maybe is also reasonably fast. The difference in runtime is incredible. Some things are like done in like milliseconds. On the same data set, other things might take hours. So you might also want to put this as a consideration in when you choose your predictive model. If you write your predictive code into RStudio in one of those files and save it, then it's great because then you can replicate it every time. You can also take the same code, just change the model parameter for another model, and you can test very easily and very quickly and consistently on the same data set, different models. Okay, how do we want to now take a model and put it into our, if we go back here, into our either Markdown document or this dashboard. And this dashboard, remember, has the Major League basketball players here and some, I guess there's a histogram, and then it has a scatter plot. What would you like to predict for a data set like this? I think one thing that's easy to see is there's a scatter plot, right? So maybe we want a line in there, like a linear regression, similar to what we had before. The scatter plot is kind of like a little more diverse here, so maybe it's not such a good model, but it's also here, this has the height of people and the weight of people, so probably a straight line in here would be a very simple thing to improve the visualization maybe. If we had here outcome variables, like how well those players play, and I don't know how baseball works, but there's all kinds of statistics and metrics that you have for players of how many home runs they have and things like that. You could actually use all this kind of information here to predict those kind of outcome statistics. And that's what all this like Moneyball, whatever sports analytics people do. They use exactly those predictive models to predict what is the performance of this player. They might even have as part of the predictive model with what other players I pair this player when they're on the field. What is the expected outcome of this player? And then based on that, they draft different players, and also they decide who plays what position at what time or when they come on to play. And they also decide what kind of training they have to do. And they do all of those things based on numbers and then those predictive models. Mm-hmm.
Question, if you're looking for what's a model here, so even for athletes, is there such a thing as middle age spread? So does your age predict your weight?
Oh, if there's a relationship between age and weight, you can actually take the data and look at it. I think the very young players are lighter than the older players, but also the very young players play different positions than the older players, which is very interesting. I think in football it's even worse, because the young players are the really strong ones that get a head injury soon and then they are not playing anymore. So there is definitely some relationship there. But once we find the relationship, still somebody who is an expert has to argue about what does this mean, and can we do something about it? Could we like feed our young athletes better and then they're not so, you know, thin? I don't know if that's the right action to take. But this is definitely where it goes. There. Okay, so this concludes actually the talk about predictive analytics, and this is really something that you have to learn on your own because there's so many different models. And I wanted to just give you the 5 lines of code that you can copy from the slides, put into your own RStudio and start playing with that. But deciding what model you really want and how you prepare your data and what variables you use. I used the weight variable in this very simple data set. For other data sets, there might be 50 different variables, and which one should be using. Maybe there's a variable that you don't have in your Excel sheet, but you know it exists somewhere else. So you have to get this variable and put it in to make a really good predictive model. That's a very difficult area. And that's why we need data scientists that understand the data, understand how to clean the data, how to bring it together, and then how to make a predictive model that really produces value, right? I'm not sure that like making a regression line here produces much value, right? But if I'm able to predict the chance that a player gets injured if I let this person play tomorrow, that probably has a monetary value that's probably in the hundreds of thousands of dollars or millions. And if I can do this, they will pay me a lot of money to do that.